Hello everyone, welcome back. If you are new, this is a new series that we have started wherein we are trying to dissect segment trees from scratch. We already uploaded three different videos on this topic in which we have discussed the basics of segment tree, basically how to build segment tree, how to do range queries and point updates, what are their time complexities and the proof of each of those time complexity, and then pseudocode and code walkthrough for each of those functions. And finally, we also looked at one of the application of point update and range queries itself. So we haven't yet discussed lazy propagation. We are just trying to strengthen our understanding of uh, point updates and range query and see how powerful this technique itself is. So I show you one particular application of this wherein you have to query something on the prefix of an array. We can also call it active inactive technique. And we have looked at some practice problem of this approach in the past. So if you haven't watched any of that previous videos yet, I would strongly encourage you to watch those videos first and then come back to this video, because this video, as we have discussed, now we are trying to just go through some practice problems from this list and solve each of them. So in this particular video, the motive is to go through this particular problem 459D of Codeforces. So with that, let's start with the basic introduction or the basic recap of the problem that we have discussed in the past video. Basically, number of smaller elements in the left. So we are given an array, and we have to, for each index, we have to count the number of smaller elements in the left. So for 6, we have two smaller elements, 3 and 1. So the value here is 2. Similarly, for 9, there are 6 elements which are smaller than 9, 2, 4, 6, 1, 3, and 8. And hence the value here is 3. Value here is 6. So you have to find this value for each of this index and return that, right? So that's the motive. Now how we approach this, so again, the complete thought process and everything, you can watch it in the previous video. I will link that in the description down below or somewhere in the top right I section. You can watch them out. To just summarize the solution, what we have done, we have just sorted this array and prepared a boolean array. Right now, let's say you have to answer for this particular index I. Basically, you need to figure out how many elements are there which are less than 6 in the left of the array. So what you will do, you will say, okay, 6 map to this particular index, right? So because this entire array is sorted, it means that everything to the left of this index would be smaller than 6, right? But we only want those elements which occurs in the left half of 6, right? So you can see there are like in the left of 6 there are 4 elements, 1 2 3 4, but 2 and 4 occurs in the right half, while 1 and 3 occurs in the left half. So you only need to consider 1 and 3 and not consider 2 and 4. So for that, what we have done is, for every element that occurs in the left half, we have marked them as 1 and others are 0. Now you can simply take a range sum in this range, and whatever the value will be, that value would give you the number of elements which are smaller than 6 and lies in the left half, because only the ones which lie in the left half are something which are active here or which are marked as 1, right? So you will keep on doing this for every element in the right. So let's say you have figured out the answer for 6, so you will just activate 6 as well, and now you will try to figure out the answer for this particular index I. So again, you will apply the same trick. You say, okay, everything in the left of 4 is smaller, so I will just do a range sum here to get how many of them are actually lies in the left half of 4, right? So again, this is just a recap. To watch the entire video, refer to the original video itself. So in this particular video, we are going to focus on this problem. Uh, let's walk through the problem statement. So this is the core of the problem statement. Basically, you are given an array of size n, and you have a function flrx, which is defined as number of indices k such that k lies between l and r and ak equals to x, right? So this is just one function flrx. Your task is to calculate the number of pair of indices I comma j, where I is less than j, and f1ai is greater than fj and aj. So let's just try to understand this problem in bit more depth. So let's take the first sample case 7 1 2 1 1 2 2 1. So that this is the our array, and we have to figure out the number of indices I and j which satisfies these inequalities, right? So first of all, this is your function f_lrx, which is number of indices k which satisfies these constraint. So k should be in the range l and r, and ak should be equals to x, right? Now you need to figure out number of indices I and j which satisfy this inequalities. So let's just try to first decode what f1ai is, or fj and aj is. So let's just try to expand them as per the definition of the inequality or the function. So f_lrx was number of index k such that k lies between l and r and ak equals to x. So let's just try to expand f1ai. Just put the values here. You will see it will translate to number of index k which lies in the left of I, right? So in everything in the range 1 to I, basically which lies in the left of I, and the value is equals to ak. So the value is equals to ai, right? So this is what the uh, value of f1iai is. So what exactly this translates to? Let's say for this one you have to find f1i, like this is I, so you have to find f1iai. So for this it means that how many indexes k are there which lies in this range, and the value of that particular element would be equals to ai, which is 1. So in this case there are two elements which lies in the in the range 1 to I, and the value is equals to 2. So f1 iai for this I would be 2, right? So hope this makes sense. What we have to do, we just simply have to figure out how many elements are there which are equals to the current element in the left of the array. That's simply what f1iai denotes, right? So in the similar way, fj and aj, if you try to expand it, you will figure out that fj and aj will also translate to exact same thing but in the opposite direction. Basically it is saying that everything in the right of j such that ak would be equals to aj, right? So basically everything in the right of j where the element is equals to the current aj. So for, let's say, this is the j, and you have to find out fj and aj. So in this range how many elements are there which are equal to 2? So there are two elements which are equals to 2, and hence fj and aj for this j would be 2. So hope you got these two function clearly, like what is the definition of these two function. So now let's just try to evaluate these two function completely. So if you try to evaluate these two function, this would be the new values of f1iai, fj and aj, right? Now how to compute f1iai? Very simple. You will just you can just keep a map and iterate from left to right, and for every I, the value of this particular index would be the frequency of that particular element. So for example, let's say we start with 0, right? Now we got 1, so we will increment the frequency of 1 to 1, right? Now what is the value of f1iai? F1ai denotes that number of indices in the left of 1, so basically in this range, which is equals to 1. So here it is 1, so that's why the first value is 1, right? Similarly, let's say you will try to find the value for I equals to 1. So in this case, again same thing, you got 2, so let's keep the frequency, increase the frequency of 2 to 1. And again, as per the definition, you have to just count number of 2's. Number of 2 is 1, that's why it is 1, right? Now for the next index, you got 1, so you just increment the frequency of 1 to 2. And as per the definition, you have to just figure out how many ones are there. There are 2 ones, so hence the value here is 2, right? So hope you got the intuition, like how to calculate f1iai. And similarly you can calculate fj and aj. For this, you just need to traverse from right to left. That's it, right? So once you have these two indices with you, notice that the original problem was you have to count the number of pairs ij such that I is less than j, and fi f1i ai is greater than fj and aj, right? So basically, let's say if j is this, right? So if j is this, you have to figure out number of i's which are less than j. So first of all, I can be anything in this range, right? And the value of f1i ai, basically the value of this array, is greater than this number. So in this case, for this particular j, number of possible I would be uh, 1, 2, 3, because there are three elements which are greater than j. So hence, for this particular j, there are three possible i's. So you can simply find out the I for each of these indexes and sum them all up to get the answer, right? So that's what the solution is. Now, what exactly we need to find out is how many elements are there which are smaller than or which are greater than a particular number x in the left of the array. So we have to figure out how many numbers are there which are greater than 1 and which lie in the left of the array. This problem is exactly similar to the number of elements smaller in the left. Only difference is you just need to count the number of greater elements. Instead of smaller elements, you will be counting the greater elements. So let's say for 6, you have to find out number of greater element in the left. You will just query this range, or just do a range sum query in this range, and you will get the number of greater elements in the left. So hope this point is clear. So what we have to do, we will just simply iterate over this array and count the number of smaller elements in the left from this array, right? So that's what will give you the final result. Now, there is one small thing here. So if you remember, we have to map, like while calculating this, we have to map this 6 to some index here, right? Now, if there are two 6, or if there is duplicate, then there will be two 6 in the sorted array as well, right? And if that's the case, you have to determine which of these two 6 you will map this to, right? So that's where you, like the previous algorithm that we have discussed in the past video while solving enemy is weak problem, will not work here, because in that video, like in that problem, we have kept a map, but map here would not be applicable. So that's where we, like simple map would not work, and we have to do something else. So again, I would, if you haven't thought it about yet, I would encourage you to pause the video and try to think how will you model this algorithm when there are duplicates in the original array, right? Pause the video and try to think about it. So the only change that will happen now is, instead of keeping instead of keeping elements, you will keep indexes as well. So instead of sorting 1 1 2 3 2 3 4, you will sort 1 comma 0 1 comma 1 2 comma 2 3 comma 3. Basically, you will keep indexes as well. And because you are keeping indexes, these numbers would look something like this: 1 comma 0, right, would be first one, then 1 comma 1 would be second one, right? Similarly, 2 comma 2 or 2 comma 1 would be the third one. Sorry, 2 comma 2 would be the third one. Now this 2 is actually this 2, so basically 2 comma 4 is the fourth one, and so on and so forth. So basically, now you can simply point to the indexes that will be your mappings, right? So that's the only difference while calculating this sorted array. Rest everything is simple. So let's just try to iterate through one example. For clarity purpose, I am removing that indexes here, and let's assume that this one is mapped to this one is mapped to this one, and so on and so forth, right? So now we are given this two array, and we need to find out how many pairs ij are there which satisfy the constraint that f1 is less than f2 or f1 is greater than f2, right? Now, first j is 0, right? So for this particular j, you will figure out, or what you have to find, you have to find the number of elements which are greater than 4. So you will just simply do a upper bound here. Now notice that this array is completely different than this array, right? So it may happen that the elements that occur in this array may not occur in this array, right? So that's where what we will do is we are only building segment tree, or we are only sorting this particular array, not this one. So what we have to do, we have to found number of elements, like this 4 may or may not exist in this array, right? So what you will do, you will just simply do an upper bound of 4, because what you need all the elements which are greater than 4. So what you can do, you can simply do an upper bound here to figure out what is the first element which is greater than 4 and which exists in this array. So in this particular case, there is no first element at all. Like upper bound will give you this particular index, and there is no first element at all. Hence, for this particular index, answer is 0. Now, as with the original algorithm, we have already like covered this j, right? So we will mark this index in our binary array. Now we will move to the next j. So we are coming to this j. So again, same thing. This 3 may or may not occur in this array. So let's do an upper bound of 3. You will get this particular index 4. So basically, you have to do a range sum in this range, right? So currently you will get 0. So the value for this j would also be 0. Now, before moving to second one, you will mark this one as well. So notice that what we are doing. Previously, we were dealing with one array only, but now we have to do upper bound on second one, but consider the first array. Why? Because we still have to figure out we still have to figure out the element which are greater in the first array, not the second one, right? So that's where we are marking, like we are, for checking the number of elements smaller than a particular element, we are checking the second array, but for marking here we are using the first array. So we'll mark one as well. Now for this 3, again do an upper bound, you will get this 4, and do a range sum here, again 0. So this will also be 0. Move forward. Now for this 2, again before moving to this, you will mark this as well. So 2 would be marked. Now for this 2, again do an upper bound. Upper bound will now give you, sorry, upper bound will now give you this particular index. So you will do a range sum in this range, and this will again come as 0. So value here is 0. Now before moving forward, you will mark this 3 as well. So this 3 would be marked. Now comes 2. So upper bound of 2, again the same value. For this, the value here would be 1. Like if you do a range sum, the range sum result would be 1. So the answer for this particular j would be 1. And before moving forward, you will mark this 2 as well. So this 2 is also marked. Now finally 1. For this 1, you will do an upper bound, and upper bound will give you this particular index. So you will do a range sum in this particular range, and you will get 3. So the value for this one is 3, and you will mark this 3 as well. And finally for this one, if you do a range again the upper bound will give you this particular index, and the range sum would be 4. So the value for this particular index would be 4, and the final answer here is 1 plus 3 plus 4, which is 8, which is, you can see the output of the um, first sample that we are given, right? So hope this entire trial run of the algorithm makes sense. Only thing that was different in this particular video, in this particular problem than the previous problem enemy in weak, was that in enemy in weak they have explicitly said that all the values will be different, but here when we have calculated this f1 I ai and fj and aj, we found out that there can be duplicates. So now we can't simply put a map, and we have to, while sorting, we have to take care of the indexes as well, right? So that we uniquely determine that which of these ones is getting mapped to this one, right? And the rest of the things were similar. One more difference was we have to, like in the original problems, we have to figure out how many elements are less than the current element, right, for each indexes. But in this problem we have to find out how many elements are greater than this particular element in the first array. So that's where we have to build segment tree in the first array, but while querying we have to query in the query from the second array, right? So hope this entire thing makes sense. Now the pseudocode would be very simple. We will first build f1 array, basically f uh, f1 this array. This is denoted by f1 here, and similarly we will build f2 array, which is fj and aj, and finally we will prepare this mapping, right? So for this mapping, as we have discussed, we will keep track of array and indexes both, and sort this particular f1 array, because we have to, we have to count the number of elements from f1. So that's why we are taking f1 and sorting it to prepare the corresponding mapping. Now once we have done that, we will just figure out the position of each of the elements here. So this one maps to index 0, this one maps to index 1, this two index maps to index 2, this 3 maps to index 4, and so on and so forth. So this is the uh, position mapping that we are building from this. Now after that, the rest of the things is very simple. We will just iterate from 0 to n. Now for each index, here we just have to figure out the first index, which in the first index in the first array, which is just greater than this. Now why we are doing this? Because this 4 may or may not exist. So previously we because we have to find the minimum in, so in this particular problem we have to find the minimum which are less than 6. So we already know that 6 will exist in the sorted array as well. But in this case, that's not the case. Uh, we have to find, we are taking this element for this array for finding the elements which are greater, but querying is coming from this second array. So the element here may or may not belong to the first array. That's why we are first doing an upper bound, right? And after whatever we get from here, we will just query the suffix part and figure out how many indexes are there which satisfy the given inequality. And after that, this is the standard part, we will just update the current index of f1 to 1, right? So hope this entire solution makes sense. If you have watched till this point, the only point of explaining one similar problem than enemy in weak was to encourage you to code this entire solution by yourself. Because unless you code this, you will not be able to understand segment trees in better depth. So I would strongly encourage you to directly pause the video here and try to code the entire segment tree, starting from the segment tree class itself by yourself, because that only will help you understand segment trees in much better depth. So next we'll look at the code. The code is exactly similar. So this part is simply the range sum. Again, some things to note here is the returned value in case of non-overlapping sequence is 0, because 0 is something that would not interfere with the original answer. Basically 0 plus x is 0. That's where we are returning 0 from here. And second thing would be that we are, like, the merging operator is plus, because we have to figure out the sum of a particular range, right? Now inside main function we are taking the array. After taking the array, we build f1 and f2 as we have looked at in the pseudocode. So we simply build f1 and f2. After building f1 and f2, we build the position array. So for position array, as we have discussed, there can be duplicates, and because there can be duplicates, we have to take both index and the array element. We'll sort it, and this map will now no longer be a map of int and int. It would be a map of pair and int, because now we have to keep track of element indexes as well. So after this, we will just initialize segment tree with everything as 0, and for each index we will figure out f1 index and f2 index. F1 index is something we will get simply from this position array or position map, and f2 index would be something that we will get from upper bound on this sorted array which contain f1, right? Uh, then once we get f2 index, we will simply do a query in the range f2 to n minus 1. Now this is important because f2 can be outside of n as well. In that case, you will not get anything. Now, if you query the segment tree for a range L comma R, where L is greater than R or X is greater than Y, this can give you weird answers. So that's where we are we are not calling segment tree function at all if it is outside. Otherwise, we'll just call tree.update. We will just call a query and sum it up with the current result, and finally we'll update the current index, right? So hope this entire solution makes sense. If you have any doubts in this problem, please post them in the comment section below. I will be happy to answer. Now, the next video, we would be finding out the longest increasing subsequence in order log n log n time using segment trees. So this problem is also one of the application of this queries on a prefix of an array itself. We will be building segment tree on some prefix and querying it on the fly. So I would encourage you to try this out yourself once, or at least think about it yourself. And in the next video, we'll look at the entire algorithm uh, in depth. So until then, if you like the video, give it a thumbs up and do subscribe if you haven't already. And I will see you in the next one. Thank you.